I think what Joe has for velocity is probably right.
Velocity A to B. Alright.
Don't worry about it.
All right,
Alright.
let's see what we got.
Yeah, okay, so for what I think the position we said it was positive from A through D, the bracket.
Okay, so the entire time?
Yeah, the
Yeah.
entire time because it was above the origin. And then
Okay,
for
let's do a dramatic pause here.
It's technically not wait, never mind, ignore me.
And this subtlety here in the fact that some people want to have it ending on the ground, but it stops before it touches the ground. So it is indeed the position is positive the entire time. So in this notation, so if you get do it in red, it would be square bracket A to D. Now, other ways of presenting it, because on the test, the last problem, I'm going to give you 4 different ways of displaying it. Just please pick one, or if that bothers you and you need to fill in more than one of them, please make sure they give the same answer. So on this grid right here, I have each of the 4 major quantities, and then I broke it up into greater than 0, equal to 0, less than 0, and so in this presentation, you would just shade in all the positives. Or in this presentation, you would just put a little plus into all of them. So all, and since it's the entire time, N-A. So those are 3 presentations of the exact same thing. Now again, on the test, pick one of these ways. Don't do them all, please. All right. Different voice. Displacement. When is the displacement positive or 0? Actually, I find it easiest, let's pick 0 first. When is the displacement 0?
A and C.
It better be at A, because that's the starting point.
Do you have to put those in brackets or no?
As in each
Separately.
one?
Yeah, separately.
If you want to put the A in brackets and the C in brackets, you can.
Okay.
There's nothing wrong with that. You can also just leave them plain. If you put A in parentheses, that's a very confusing message, so
Right.
please don't do that. But it sounds like what you did is fine. So in this chart right here, we have displacement is 0 here, and it's 0, oops, 0 there, and there. All right, when is it positive?
It's positive from parenthesis A to parenthesis C.
Yeah. So it starts out at the starting point, almost by definition, and then it stays above it in the positive side of it until it gets back to its starting point. And so it is positive in between there, or A parenthesis, A, C, close parenthesis. And so positive, positive, positive.
Question.
Yes,
Why is that parentheses not brackets
where?
for positive displacement?
Either.
Yeah.
Is the displacement positive at A?
No, no, because it just started.
Yeah, that is the starting point.
Oh, right.
So that's, so A is not included, and the same thing at C.
Okay. Yeah. Okay.
But if it's the time after, like the ball's not in his hand though.
It's not.
If the starting point is the ball in his hand,
The starting point is not.
Yeah.
The starting point is just after the ball left his hand.
okay.
Which is A.
All right. right, and when is it negative?
C,
Bracket C to
C to
D bracket.
D, no, C is not bracket. No, it's a parenthesis for C.
Which one's bracket, which one's parentheses?
C is parentheses, D is bracket.
There we go.
Now, I can see this very clearly here, in the back of the room. Does the red show up well enough?
Yeah.
Okay. So if you put a bracket here for C, that means you're including C here, but you have C here also. Try not to put something into two categories at once. Again, RIPs in the space-time continuum, out of scope for this class. An object will not be in more than one category at a time. So it's negative there. Velocity. Oh,
the negative zone.
Bracket A, parenthesis B.
Bracket A, bracket C, for positive.
Bracket
Yup.
A, hey, close, parenthesis B.
Yep.
Parenthesis B.
Is that what you said?
Parenthesis B.
Okay, let's try that again. What's happening at B?
It stops.
Okay, so B is 0.
Yeah.
Okay. So I think I just misheard you before.
Yeah.
So bracket A,
Parenthesis B.
parenthesis B,
Yeah.
and that's it?
And then for,
It's negative from parentheses B bracket D.
yeah,
So you have it positive from here to here, 0 at B, and then negative the rest of the way. So you have positive, positive, 0, negative, 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 negative. Okay? That is correct.
So was it not clear that the ball stopped at D?
That the ball stops at,
D?
the ball does not stop at D, because it's just before it touches the ground.
I'm probably just confused, but when it's, even if it's technically going down, it hasn't dropped below the origin, so doesn't it still have a positive velocity? It would just have like a,
Remember that we're talking about the default is instantaneous velocity.
right,
So since it's heading downwards, it's negative,
okay.
because I made it positive. All right, and any other questions up to here before we tackle what some people find the most confusing? Jackie, you look like you want to ask a question. All right, acceleration. Got the same two voices again. I don't wanna- All right, there we go, Brian.
That's always negative.
Yes.
So from bracket A to bracket D.
Surely.
on a single,
Add something else.
or just take it.
I get that, but I put B as 0.
All right, that's the most common mistake there. Acceleration deals with change in velocity. Do you accept that the velocity is 0 at B?
At max, yes.
Yes. So if the acceleration is 0 also, that means the velocity won't change.
Meaning it's constant, meaning acceleration would be 0.
No, let's try that one again. At B, it stops, because it's turning around.
Okay,
If the acceleration is 0, which I heard you say that's what you were thinking.
yes.
If the acceleration is 0, then the velocity does not change. So if the
Okay.
velocity is 0 and does not change, that means the velocity will stay at 0. Which means you throw the ball up, and it would stop and hover.
Right, at point B, that's what it does though, at its peak, right?
It stops, but it doesn't hover. It stops and then comes immediately back
Right,
down.
after it leaves B.
At
I'm
B,
just trying
it's,
to understand. Because if you're saying that, because we're just talking about point B, so at point B, the velocity is 0.
that is
right?
correct,
Okay.
but it doesn't stay 0.
Right, but at point B it does, so,
That you can't have a,
because it's
you
constant.
can't talk about change at a single point in time. You have to look at that moment and then just before it or just after it. I hope that explanation doesn't bite me in the butt later, but.
Yeah, I don't get it.
It's like,
Heisenberg.
on B being zero is only pertinent for velocity, right?
Right, but because it changes, acceleration is not zero.
Yeah.
Because it's not but B because the velocity was, no, not the acceleration was still negative, so it just like slowed down the velocity to zero, but the acceleration never stopped the effect of falling down.
Like a constant velocity is something that.
But it's
moves.
constant at B, velocity.
If velocity is constant at B and it's not moving, then it stays at zero?
If it's,
The velocity isn't constant because like it changes at all, right?
No,
if you're saying, but we put for B, that B, for velocity, that B was zero.
The velocity
Maybe I
is
just
zero
don't-
at B, yes,
Right,
I agree. But just because it's not moving doesn't mean it's not accelerating.
but not moving means constant.
No,
Oh, okay.
not moving is a
In
split.
this, in this situation, I know.
Yeah, I mean, you can have something that is not moving and acceleration is zero, that is possible. But because that the velocity is constantly changing throughout this trip, acceleration is not zero at B.
Yeah.
Because acceleration is the rate of change of velocity.
So due to the fact that it's changing at all, there is an acceleration.
I almost feel you've gotten to just nodding your head, you can be done with it.
Well, I just don't get it, so it's
Okay.
okay.
We're gonna look at it a slightly different way and hopefully that might clear some of it up.
Yeah.
So like, in a hypothetical, if it goes from A to B, and then it goes from B to nothing over a significant amount of time,
As in it stops at B,
yeah, then it would be
acceleration.
Like a
constant there
fucking
for
minute, then it probably doesn't
a
have-
minute, or however long that time frame is before, I'm not saying that's possible, I have no idea, but before it then drop back down. Like,
Yeah,
if it was
it-
just hovering there for
If it hovered there for a brief moment, I mean, longer than
split
a
seconds.
single moment in time, it was there for 2 moments in time in a row,
Okay,
then you would say acceleration is zero.
Like if there was like a
Okay.
B2,
Pardon?
if there was a B2 where it was also zero.
Yes,
okay,
that take whatever Planck time later.
that would be like B2 would be zero, velocity zero acceleration.
Yes.
Okay, I get it.
Now,
So if you're in a swing set, you go up, you have a brief pause, and then you go back down. At that point, it's like you're not accelerating or.
if there were a brief, let's say brief pause, that still takes place over 2 consecutive moments in time.
At that point, B.
Then, if that happened in B, but at B, it's not there, it's not stopped for 2 consecutive moments in time, it's only stopped for a single moment in time, which means it's not zero just after and just before, which means the velocity is changing.
Yeah.
All right, let's take a look at it a different way and, oh, sorry,
I'm sorry, but I don't understand though how from point A to B, well, point A to D, it's negative. Cause I would think that from point A to B, the acceleration would be positive, and from B to D, it would be negative.
why do you think that?
Because you're going up, so you're accelerating,
But
and you're dropping down, so you're way.
I think you're confusing velocity and acceleration, which is also a common issue. All right. Let's take a look at it from a different point of view. Acceleration, this isn't gonna help, this is not gonna help you for that, what happened at B, but it's gonna potentially help Nayeli in this case. As it goes from A to B, is it speeding up or slowing down?
Slowing
Slowing
down.
down.
I hope so. If you throw something in the air and it starts speeding up, then I guess it has a rocket engine or something. So from A to B, it's slowing down. We established some color that would just pop. So from A to B, we said the velocity was positive, but since it's slowing down, this will be the opposite sign. From B to C, it is speeding up, slowing down,
Speeding up.
speeding up. Since my So from B to C, since my velocity is negative and it's speeding up, it's the same sign. From C to D, it's still speeding up, one would hope, and so they're the same sign. So up, these are speeding up, signs are the same, this is slowing down, the signs are opposite. Now, it doesn't address the issue of what's happening at the turnaround point.
Yeah.
Another way of looking at acceleration, and even though we have not talked about it in much detail, but it's also in the direction of the net force. So once this has left the hand and it is in the air, there's no air resistance, but let's assume that there's still air. So for the trip, name all the forces acting on it.
Gravity.
All right, I'll nitpick that one later, but yes,
Well, you just said there's no air resistance, right?
correct.
Drag.
No,
That's
is it,
air resistance.
is it the
I was
force,
wondering if anybody was gonna throw in
the
Jedi
force
powers.
that you use to throw the ball up?
Jedi powers.
No.
We will assume for the sake of this course that Jedi powers do not exist, that I cannot manipulate something after it's left my hand of any significance. So therefore, whatever force the hand exerts on the ball stops as soon as the ball leaves it.
Inertia.
Not a force. All right, it is just gravitational force.
Okay.
The weight of the ball is the only force acting on it. Which way is that weight acting on the ball?
Down.
Yes. And since that, is there at any point when the weight is not acting on the ball?
Nope.
Therefore, since the force on the ball is down the entire time, the acceleration is down the entire time. Slightly different way of looking at it. And generally, looking at the forces is the easier way of dealing with the turnaround points. Now,
Can you give me an example of the acceleration being up the entire time?
Just like a ball.
well, if there were no gravitational forces in the leaves the hand, it'd be a constant velocity. And
Zero acceleration.
do
There's a rocket.
you want a realistic one, or do you want anything? Because we can do this on a board.
I should have said realistic.
As soon as it leaves the hand, a piece of a neutron star shows up right above it. So the gravitational pull from the neutron star is greater than the gravitational pull from the Earth, and so it would start getting faster.
I see.
It would not come back down though.
I just
I wouldn't do everyone a favor and not ask why.
Neutron star densest material of which we know.
Right, yes. Obviously.
So accelerating too.
All right, we're gonna take a look at this a different way. Questions before we look at the graphing? Because everyone loves a graph. Seeing some nods out there, some people are in agreement.
Mine was sarcastic.
Okay. Something I started a couple years ago was once you did this part, the next part was to represent it in a graph. So I'm gonna plot position, velocity, acceleration, then we'll talk about what the displacement graph would look like. But if I have a position versus time graph, I know that it has to correspond to what I have over here. It has to be positive when this is positive, it has to be negative when it's negative, and zero when it's zero. It's positive the entire time. So whatever I do here, I know that it's got to be positive. Now, I know that it starts here, it goes up to some point, and then comes back down. Never quite touches the axis, because it's positive the entire time. And as with the convention, I assume that the horizontal axis hits the vertical axis where the vertical is equal to zero. My velocity time graph, it starts out positive, and then it's zero at B. So this would be B, A.
What it represents is positive, or position.
Yeah.
Yeah. Okay, well.
Do that. So A, B, C, D. Oh, there's no E. So it peaks here, so it's basically this kind of maneuver. Now, it's gonna be a little bit awkward in the drawing of it, and so the instructions on the test are sketch. It doesn't quite hit there. Because on the test I have this set out, but these time increments are actually not the same. That C to D is a shorter time frame than A to D or B to C. So just be aware that it's gonna look a little bit wonky. My velocity I know starts out positive, it slows down at B. It's 0, so I'm gonna put that down, it starts out positive. And since the force acting on the ball is constant, or close enough for anything that we would ever do, acceleration would be constant. So my acceleration graph is going to be negative the whole time. I went too far. Now, one of the reasons I did not have it touch the ground is once it touches the ground, we've introduced another force to the ball, and so the acceleration gets really funky, and we'll hit that kind of thing in the next problem. So when I grade this part, one of the things I'm looking for is does it match what you have over here? All right, so that would be consistent. So I'd write a little C with a check mark saying it's consistent. The next thing, is it self-consistent? I know that the velocity is the change in the position over the change in time. In other words, the slope. Well, as I look at this, in this region here, is the slope positive or negative? That's only just whispered it.
Positive.
Yeah, so my velocity is positive. At B, when I'm at that peak there, my slope is
0.
and then after that, my slope is
Negative.
all right, so it's self-consistent. It's positive when that slope's positive, 0 at the peak, and then negative. And down here, my acceleration, well, I drew this as a straight line just because I know it's supposed to be. Drew that as a straight line, that should be negative.